So welcome back to my next webinar on C++ Standard Template Library by example. Today we're going to finish off our discussion of C++ STL iterators. The last couple of days we've talked about an overview of iterators. Then yesterday we talked about input, output, and forward iterators. And today we're going to finish up with the other two types of iterators, which are bidirectional iterators and so-called random access iterators. So as always, before we begin, let's take a look at where you can find the source code. So you'll be able to find the source code for this particular discussion in my C++ folder in my GitHub repository in the 4.6 and 4.7 subfolders. So we'll start our discussion with examples of bidirectional iterators. First, what is a bidirectional iterator? Well, a bidirectional iterator is essentially a forward iterator. It has all the same methods and operator overloaded methods that a forward iterator has, plus two other elements, and that's the ability to go backwards, either with pre-decrement or post-decrement. So these are the plus operations. So just to kind of recap what a bidirectional iterator can do, it can do copy construction, it can do assignment operation, it can do equality and inequality. You can dereference it on either the left-hand side or on the right-hand side. And then you can do both the plus operations with pre and post increment and the decrement operations, pre and post decrement. So you can do quite a number of things with a bidirectional iterator. All of the STL containers, with the one exception of forward list, provide bidirectional iterators or better. The better being the random access iterators we'll talk about next. So the vast majority of the built-in STL containers, the ones that come out of the box when you get STL, those all come with bidirectional iterator semantics. Keep in mind that input, output, and forward iterators only let you go forward, only let you do plus. But because we have the ability to go backwards, you can go bidirectionally. So let's take a look at how we could use bidirectional iterators. And this is kind of a fun one. We're going to go ahead and create a list that initially has one element in it, and we're going to give it the initial value of 1. Then we're going to go ahead and put some elements at the end, or put one element at the end and put an element at the beginning. And to do that, of course, we're going to use the PushBack operation to put the element at the end, and the push-front operation to put an element at the beginning. And that all works very efficiently, of course, because the list supports efficient insertion at the beginning, at the end, and also once you've moved your way through the list, through iterators, you can also insert things very efficiently anywhere in the middle of the list, because it's just about reconnecting the pointers. So now that we've got ourselves this list, which has basically 0, 1, 2 in it, let's go ahead and use some iterators to print the contents of the list in reverse order, or print it backwards. And we'll show a couple of different ways to do this. First, let me just go ahead and run the code so you can see exactly what it's doing. So it's going to go ahead and compile, and it's going to print 2, 1, 0, which of course is the reverse of the contents, which are 0, 1, 2. So let's see how it does this. The first thing we're going to do is we're going to get an iterator to the beginning of the list using the explicit iterator syntax. We've talked about this before. This is using the trait, the iterator trait that's associated with every container. And then just for kicks, just to make things different, just to show a more concise way of doing things, we're going to use the auto keyword. So this is going to get us the last iterator, an iterator to 1 past the end, using the end factor method. And we're going to store it into a field, into a variable called last, which is an auto. And then, while last minus minus is not equal to first, we're going to print out the last element. And there's a whole bunch of different ways we could do this. So this particular approach starts at the end, and notice how we decrement it with a post decrement each time through. We don't have to do it that way. We could also have done it like this. We could have said, while last not equal to first, cout star minus minus last. The key point here is that we can never access the last iterator, the iterator to the end. We always have to decrement it by 1 before we can actually access its values. And that's because the iterator to the end never really points at anything. It's just a placeholder to be used in a comparison way. So we can either do it like this, or we could do it like this. There's a couple different ways we could write the code. So that's an example of being able to use a bidirectional iterator and demonstrate how you can go backwards in a list and print the contents out. Okay, let's go ahead and look at another example. This example is also illustrating bidirectional iterators. And this is also going to show off some other interesting things with C++. Up to this point, when we've been putting elements at the end of a list, or putting elements at the beginning of a list, or putting elements at the end of a vector, we've been using the pushback operation. And pushback works quite nicely, and it works very optimally for built-in types, things like int and double and so on. When we start getting to user-defined types, types that have various types of constructors and conversion operators and so on, it turns out that pushback is not necessarily the right thing to do and not the most efficient thing to do. So in addition to demonstrating bidirectional iterators in some pretty cool ways, this approach is also going to illustrate the use of a variant or an addition to pushback, given the strange name of InplaceBack. And InplaceBack is going to use some cool fancy footwork in order to make the insertion of elements at the end of the list, or the end of the vector in this case, more efficient. So I think I take it back, we use a list in this case. But it wouldn't matter, the vector would be the same. So what we're going to do is we're going to start out with a list of so-called simple strings. Now, what is a simple string? Simple string is a cool little piece of code I wrote to, cool little class I wrote to demonstrate a bunch of interesting aspects of C++. And we're particularly going to be using it to talk about move operations and various optimizations you can do with C++ and its move optimization semantics. We'll show some other things too. For example, here we're going to show the use of simple string in the context of automatic conversion from one type to another. So here's what simple string is. It basically just implements a stripped down version of C++ string, but it's not fancy. It doesn't have all the methods a string does, just the ones I need to get the point across. So as you can see here, we have a default constructor. We have a conversion operator that takes a const char star, like the string literal apple or peach or banana, and turn it into a simple string. And you'll see why I don't actually make this explicit later, because I want to do some cool stuff. We also have a copy constructor, which does not throw an exception. We have something called the move constructor, which we'll talk about later, which is really cool. We're going to have an assignment operator, which also does not throw an exception. And we have what's called the move assignment. So we have copy constructor, we have a move constructor, we have a regular assignment, a constref assignment operator, and a move assignment operator. And then we're going to have a couple other methods just to illustrate certain things, like a swap method, a couple of operator subscript methods to index into the simple string, a less than operation, a length operation, a destructor, and then we also here have a conversion operator that converts an object of simple string into a const char star. And you have to explicitly make cast in order to do that, but you'll see how that works. The implementation of our simple string is pretty simple. We have a length field. We have a char star that's going to hold the buffer that we're using as our simple string implementation. And we have a little helper method called stir new, which takes a const char star and makes a char star using the underlying C++ code to do that. Last thing I'll show you from an interface point of view, we have an extraction operator that's able to take a simple string and print it or insert it into the IO stream. Okay, so now let's take a look at the implementation of this stuff. So you can see here how we're able to have this operation that basically takes this simple string and explicitly casts it to a const char star. So that's going to actually end up calling the method here. So it's going to go ahead and return the underlying char star, and we use that just for printing purposes. And then down here we have the different implementations. Now I'm not going to spend a lot of time on the implementations related to move semantics at the moment. We're going to cover those in more detail later. But for the starting point, I just want you to see how we've instrumented all the various operations so you can tell what's going on under the hood when we run them. Obviously, production code would not do this. This is just for teaching purposes. So here's the simple string constructor, and it's going to set the length to 0 and set the stir to a null pointer, which is a keyword that's been added in C++ 11. And we print out the fact this is the default constructor. We have a conversion operator that takes a const char star and creates a simple string, and you can see it goes ahead and figures out how long the const char star parameter is, and then it makes a new instance a copy of that string, and here's all it's doing. It's basically doing stir len here. I guess I don't really have to do that. That's probably duplicative. Then we go ahead and copy the old string into a newly allocated string that's big enough to hold the length plus 1. All right, so down here, and then we print out the fact that that's the conversion operator that takes a const char star and makes a simple string. Next thing we have is a copy constructor. As you can see, what the copy constructor does is it takes the right-hand side and it goes ahead and initializes the left-hand side, the side we're creating, the simple string we're creating from the contents of the right-hand side, and prints out it's the copy constructor. And then down here, we have something called the move constructor. We're going to talk about this later. Move constructors are very clever, and they're used in situations where you want to optimize value semantics in C++, especially in situations where you don't really need to keep around the contents of the string you're moving from by value. So for right now, we won't talk about this a whole lot, but just note that we indicate we're using the move constructor. Here's the canonical way to implement the regular good old assignment operator. Notice how these things are all no exception. They're tagged by no exception keywords, meaning they don't throw exceptions under any circumstances. And so here we check for self-assignment, and then we go ahead and do the classic safe move operation, the exception safe move operation. We make ourselves a temp copy of the right-hand side, and then we swap that with the left-hand side. And so this is a clever technique. We'll talk about this more later too. Here's the move constructor, the move assignment operator rather. Here's a swap operation that just swaps the lengths and the stirs in the values that are passed in. Subscript operator just indexes in there by the index that's passed in. That's just good old sort of array indexing or vector indexing. Length returns len, and then less than does a stir comp and checks to see if the value is less than 0. That's how we do less than using these kind of C-level type strings. And then finally, we have our destructor, which goes ahead and deletes stir, which could be null. Deleting a null pointer is perfectly fine. We have to delete it as an array because that's what it is. It was allocated as an array. And then if for some reason stir was a null pointer, we just print out the fact it's a null pointer. Okay, so that's a quick overview of simple string. Now you might be asking, what the heck does this have to do with bidirectional iterators? And what the heck does this have to do with InplaceBack versus PushBack? So we're going to get to that here. So what I'm going to do is I'm going to go ahead and call InplaceBack to put peach, apple, and bananas at the end of the list in that order. So peach goes first, followed by apple, followed by bananas. And you'll see when we run this thing, those are the order that they're going to show up in. Then just to compare and contrast this, I go ahead and I push back peach, apple, banana using the pushback operation instead of InplaceBack. So let's go ahead and run the code, and we'll see the difference, which is really quite startling, between these two things. So here's the operations that are done on a simple string by the InplaceBack calls. And you can see they're really concise. All we're doing is we're creating a simple string from the const char star parameter that's passed in, namely this parameter, these character literals, and those things are being directly stuck at the end. No muss, no fuss, just those calls. That's why InplaceBack is so useful for these user-defined or more complex non-primitive types. In contrast, look what goes on with simple string when we do pushback instead. Same outcome, we end up pushing those elements onto the list in the right order, but there's so much more work. First, the pushback call creates a simple string from the const char string. Then it goes ahead and it does the move operation, the move constructor. Then it goes ahead and calls the destructor, even though it's a null pointer. It just has to call it as part of the semantics of C++. So you can see that for every operation that was done up here for InplaceBack, we have triple the number of calls for pushback. And you might ask, well, what the heck is going on under the hood? So if you take a look at InplaceBack, you'll see why it's so much more efficient. What it's doing is it's using the variadic template features that C++ defines, which we've talked about before. And so it's going to take this variadic template of arguments, and then it goes ahead and it inserts them at the end of the list, and it uses the magical std forward method. And what std forward does is it just goes ahead and kind of copies those methods without doing anything to them at all. It doesn't do any additional calls, and it just goes ahead and inserts them in place. So of course it's going to be very, very efficient. As you saw, it just calls that one operation. Conversely, if you go look at pushback, pushback is not as clever. And what pushback does, pushback takes an R value reference type, and it goes ahead and does a move operation. And as you can see, that's pretty efficient because it does call the move constructor, and the destructor then has nothing interesting to do, but there's additional calls. So wherever possible, when you're confronted with a choice between using InplaceBack versus pushback, it's usually a good idea to use InplaceBack, especially when you're dealing with user-defined types or standard containers that are non-native, non-built-in types. For the built-in types, it doesn't really matter. But when we start getting into the user-defined types and the standard containers, then it does matter. All right, so that was a very long-winded way of talking a bit about some cool differences between methods in C++ that use variadic templates versus those that use move semantics. And these variadic templates were added later. It came, I believe, with C++ 11, and you can see it helps to make things more efficient. Now let's get back to iterators and bidirectional iterators. So what we're going to do here is we're going to make ourselves another simple string, given the incredibly boring name of y, and why not? So we're going to make a list of simple strings called y. It's going to have the same size as a list, the one we just pushed elements into. And then what we're going to do is we're going to go ahead and call the reverse copy algorithm. And let's go take a quick look at reverse copy. What reverse copy does is it goes through the iterators in reverse order. So it has a first iterator and a last iterator, except it's going to go basically in reverse order in how it treats them. So what it does is it's going to go through while first doesn't equal to last, but every time through it's going to decrement last by 1 and then dereference the decremented last, storing that into result. So it's going to go ahead and go through the input iterators in reverse order, which is why it's called reverse iterator. So if we come back over here, you can see we're going to start at the beginning we're going to pass in the beginning iterator to the list, and the end iterator, which is of course always 1 past the end, to the list. And then we're going to pass in the beginning iterator to the new list we created called y. And then reverse copy will copy them from the end to the beginning. And then we go ahead and print the results. Now the print results thing here is a variant of what we looked at when we were talking about output iterators, where we're going to go ahead and copy from the beginning of y to the end of y, and we're going to go ahead and use this OStream iterator adapter to write each element in y to standard out. So this is just that adapter code we looked at before that makes sure it gets written to standard out using a space as the delimiter between each element we write out. And then just for kicks, just to show there's yet another way to do this stuff, we're going to go ahead and use the same copy algorithm we did before. We're going to copy from an input iterator to an output iterator, except this time we're going to print the results backwards by starting at the end and going to the beginning. So rbegin is used to return an iterator. It's called a reverse iterator that goes from the end to the beginning, and rend is used to return an iterator that is indicative of the beginning of the elements. So those are what are known as reverse iterators, and they're actually quite cool as well. We'll take a look at reverse iterators in more detail later, but you can see that rbegin creates a reverse iterator at the end, and of course rend will, let's go ahead and see what rend does. If we look at rend, you can see that rend is going to return a reverse iterator to the beginning. So they're basically just reversing themselves. So I think I might have run this already, but if not, let's run it again, focusing this time on the output. And you can see the output originally is bananas, apples, peach, bananas, apple, peach. That's in reverse order because we started out with peach, apple, bananas. And then we go ahead and print that in reverse order. And now it's going to be peach, apple, bananas because we're doing the pushback operations here. So pretty darn interesting, if you ask me. This example shows off all kinds of cool stuff. It obviously shows off the concept of bidirectional iterators and the ability to do reverse copy and the way to do different ways of reversing things and printing things out in reverse order and so on. And then it also shows us the difference between InplaceBack and PushBack. And you can see that the compiler is really trying to get us to convert PushBack to InplaceBack. So if we go, yeah, tell me what you want me to do, compiler, it says use InplaceBack instead of PushBack. Now I'm choosing not to do that because I wanted to demonstrate the difference between the two approaches. But you can see that the compiler and the interactive development environment is really trying to move you in that InplaceBack direction, which is good because it's going to be more efficient. Okay, so that's the end of our discussion of bidirectional iterators. In the time that we have remaining, I would like to focus now on random access iterators. And these are the most powerful form of iterator. You can use random access iterators with vectors. You can use random access iterators with decks. Those are really the key built-in containers that use random access iterators. And they can basically work like regular good old pointers with regular good old pointer arithmetic. The difference being, of course, that they're implemented at the user level, not the compiler level. And so in addition to everything a bidirectional iterator could do, all the stuff that we saw, then random access iterators can also do all of these other things. So all of these other things are actually more than what a bidirectional iterator can do. Remember, a bidirectional iterator can do assignment, construction, not equal, equal. It can do dereference. It can do plus, plus. It can do minus, minus. But a random access iterator can do plus, plus equal, minus, minus equal, subscript, and then all the other relational operators like less than, greater than, less than and equal to, greater than equal to, all that kind of good stuff. So here is the vector class that provides random access iterators that can be used as we show here. So we're going to create a vector of 10 numbers, 0 through 9. Pretty straightforward. And then we're going to go ahead and we're going to iterate through this vector, and we're going to skip over the odd numbers. Now this, of course, is taking advantage of the fact that I really know how my input is laid out. So it goes, 0, 1, 2, 3, etc. So what I'm going to do is I'm going to start at 0 at the first location. I'm going to take that value and I'm going to add it to the 0th iterator. Then, as you see here, I'm going to use the plus equal operation to skip over the odd numbers. So I'm going to skip over them. So I'm going to skip over the 1, 3, 5, 7, 9, and just sum up 0, 2, 4, 6, 8. And of course, if I go ahead and run these, as I'm doing here, you can see that I get the sum that I would expect. And what's interesting about this, I probably should have done this before. Let's go ahead and do 2 versions of this, much like we had done in previous examples, where this time we're going to create an array of 10 numbers. So let's go ahead and do int, and we can't call this A, of course. Let's call it, or we can't call it V, let's call it A. And let's go ahead and assign it what it needs. And then we can use the same code here. Now, in this case, we're not going to be able to use an iterator. Instead, we're going to go ahead and use I, and we're going to say A, and we're going to say I not equal to A plus, and then it's basically going to be size of A divided by size of star A, which is admittedly kind of awkward and obnoxious, but that's just the way it works. Let's see. And then what we're going to do here, whoops, we got to add this here. And then we're going to say I plus equal to 2. Oops, sorry, this should be an auto. This is actually going to be a pointer. And so star I. Maybe I should call this IP. That's a better way to call it. IP. And let's go ahead and do a little bit of refactoring here just so the code isn't quite so ugly. Let's call this int A size equals, and let's go ahead and give it this expression. So you can see that that's the size in terms of the number of elements, if I could put my parentheses correctly. And down here we say A plus A size. And there we go. I think I got that. So now we have the same basic code that we did before down here with vectors, except now we're going to use built-in types. And so what this is showing is that random access iterator look and feel, the syntax, the semantics, is basically equivalent to pointer arithmetic. And what we're doing here, of course, is pointer arithmetic. To make this more clear, let's just call this int star. I think that's a little bit more clear. I could say auto, but that's kind of hiding what's going on under the hood. So very cool. Let's run this thing. Unless something is very, very, very strange, we should get exactly the same results, which we do. The sum of the even numbers using the built-in array is exactly the same as the sum of the even numbers that are using a vector. And the code, as you can see, is very, very, very similar. And again, if I use auto here and do a few other little futzes, it'll be even more cool. Okay, so that was an illustration, one illustration of several that demonstrates the use of random access iterators. So now let's go ahead and show some other uses of random access iterators. And once again, we're going to compare and contrast pointer arithmetic ways of doing things with the way in which random access iterators work. So let's take a look at the pointer arithmetic version first. We're going to have an array of 4 ints, 1, 2, 3, 4. And now we're going to show first pointer arithmetic. We're going to create ourselves a couple of pointers. Again, it's probably better to do explicit pointers here just so it's clear. Otherwise, we kind of lose type information. So you can see here that we're creating an int pointer that points to A, and then we go ahead and take that int pointer and we add 2 to it. And then we're going to print out the contents, which of course should skip over to print 3. We perform some pointer arithmetic. We add 3 to I, and we're going to go ahead and print that out. So that'll print 4. Then we go ahead and subtract 1 from I and assign that to J and print that. Then we do J minus equal 2. This is all wonderful pointer arithmetic magic with the C style parts of C++, print that out. And then down here, we go ahead and say, is J less than I? Remember, these are pointers we're comparing. If J is less than I, then we go ahead and print J less than I. Otherwise, we print out we're not less than I. So we basically do that. And then we do some other things to check equality. So that's how we do the pointer arithmetic version. Let's just run this code to kind of see what it's going to produce as output. And as you can see, for both versions, both the pointer arithmetic version and the vector version using random access iterators, the results are the same. It prints the values out after we mutz around and change the contents using pointer arithmetic or iterator operations. And then it also does some equality and inequality and relationship comparisons. And if you look down here, you can see that the use of vector with iterator gives you basically exactly the same code. The only difference being that, you know, I guess if I really wanted to make this stuff look alike, I probably should revert back to using auto here. So let's say auto I, and we'll say auto J, and then that code is going to look a heck of a lot more like the code you see down here, where we're getting a beginning iterator using auto I, and we're then advancing that iterator by 2 to make auto J. So if you look carefully, you'll see that the code for both cases is literally identical except for creating the vector and then getting an iterator to it. All the code down here is identical between the iterator version and the pointer arithmetic version. And that's by design. Random access iterators are meant to mimic the syntax and semantics of pointer arithmetic. Okay, so that's yet another example. Now let's go ahead and take a look at example 4.7. And here you can see that we've got, once again, a random access iterator example and a pointer arithmetic example. And for some strange reason, I put the random access iterator version first. It doesn't really matter. So let's take a look at the random access iterator version. I'm going to make a vector of strings using the string initializer syntax, the vector initializer syntax for basically what's effectively an array of strings. And then I go ahead and print the results. So of course it's going to be A, B, C, D, E, F, G, H, I, J. Those get printed with new lines separated. Let's be sympathetic to ourselves and put space here, not a new line, because otherwise things tend to run off the end of the screen a bit. And then we start doing some other fun with iterators. So we get an iterator to the beginning of the vector. We increment the iterator by 5, then we subscript into the iterator at that location it's been moved to and add a 1 to it. So now it's going to refer to it's going to change the contents that's in the string. Then we go ahead and we zip back to the start by subtracting 5 from the iterator. And then we go ahead and we print the results, starting at P, which has been moved all over the place from the beginning and made a change here. And then we go ahead and move it back to the beginning. So just demonstrating you can use kind of random access operations on this iterator. And then down here is basically the same code, except this time we're going to be using pointer arithmetic on a built-in array of const char stars, which are effectively the string-like substances when you're working with the C aspects of C++. And as before, we can copy the results, and then we can go ahead and do a bunch of funny things with pointer arithmetic, except this time we're truly doing pointer arithmetic. We're not dealing with iterators at all. And once again, we print the results. So let's go ahead and run this code, and I think you'll see what it's able to do. I think I also forgot to replace the spaces with the new lines with spaces. So you can see it prints this content out, and then it does some stuff. Notice it replaces, it puts a Z in there. So A, B, C, D, E, F, Z instead of G, but otherwise it's the same. So I'll have to go back and futz around with the example here. So I get rid of the new line, and instead we're going to use a space. Let's just do that real quick. That won't take us very long. Let's get rid of that new line. I don't like the new lines because they tend to make the code hard to read when you're running it here in this context. But let's do this to see how. Now while you run it, it should be a lot more coherent what we're doing, and you'll see that things are working the same way. So we print out A through J, then we go ahead and modify element G using in the first case, using the iterator and the random access features to go and make that change. And then down below, we do the same thing, except this time we're going to use the built-in operations with pointer arithmetic as opposed to using the iterators that come out of the box with STL. But all very cool, all very interesting, showing you how comprehensive C++ random access iterators are in terms of mimicking the syntax and semantics of pointer arithmetic, with all the good and bad that implies. So those are the main topics I wanted to cover today. Let's go ahead and stop screen sharing. We'll see if anybody has any questions. If there are no questions, I'll give you a quick overview of where we're headed next. So at this point, we have now completed our coverage of STL iterators, and you should now be very familiar with all the different kinds, the input, output, forward, bidirectional, and random access. And we've also talked about containers. So we've talked about sequential containers, things like list and vector and deck and so on. And what we're going to do starting tomorrow is we're going to begin our discussion of so-called associative containers. And associative containers are in some ways more powerful and also more complex than the sequential containers. And the main reason that they're more powerful is that they give you the ability to order the results, at least the ordered associative containers do. And we'll see that there's a couple different variants. There's sets, which have only a key. There are maps that have a key and a value. Sets and maps must have unique keys. Then we also have multi-sets and multi-maps. And as the name implies, those can allow duplicate keys because it's multi. And we'll see how these different types of ordered associative containers store their contents using essentially a balanced binary tree called a red-black tree. And then we'll also talk, probably not tomorrow, but perhaps on Friday, we will cover how the unordered associative containers work. And unordered associative containers have the same basic types of semantics in some ways. They've got sets and maps and multi-sets and multi-maps, all of which behave pretty much the same way as the ordered containers, or ordered associative containers do. The big difference, of course, being that the unordered containers don't use red-black trees as their implementation data structure, and instead they use hashing. And so as a consequence, hashing doesn't order anything. So they're ordered however the hash function will order them. So we'll talk more about that, and you'll get a chance to learn how the different containers are implemented. So that's what I wanted to cover today. Thank you guys again, as always, for joining. Feel free to like and subscribe, and feel free to follow me on Twitter if you'd like. And with that, I will talk to you very soon.